Good. I think we'll make a slow start whilst people still wander in. This is normally what I call the Grace Yard session. It's a Saturday, it's after lunch. So, but I've got something entertaining for you coming along, so hopefully we can get you sort of woken up again. Anyway, you are probably here because you want to hear something about building native code, and you wonder how you can do this with Gradle, which is normally known as something for building JVM applications with. So we'll talk about that. Firstly, about me. Some of you know me for years, unfortunately. Maybe you say, I don't know. So my name is Schalk Cronjé. That's my Twitter handle. You can reach me on a variety of email addresses, but that's one of them. That's me out walking. You could have guessed that. So I live in a small country, all the way up there between Spain and France, called Andorra. I made that move more than just over a year ago. Decided I wanted a better lifestyle. So that's what it looks like in winter. Obviously in summer, it's a brilliant place to be in as well. So now you know about me. The other thing I've done, I've written some books. I am in the process of finishing some other ones off. So I've done a book on Gradle, and a second one is nearly done. I'm also working on another book on continuous build and integration and how it fits into the DevOps cycle. Yes. So all of the things that I'm going to talk about today is all on GitLab. I'm following sort of a script here, and you can also pick this off GitLab as well. That's the URL. YSB33R, gitlab.io, native Gradle. So this is actually a thing I've written to act as a guide for people who want to work with native code with Gradle. And it gets added to, so you can actually use that. So I'm going to make that disappear as well for now, for the moment. Okay, so the one thing that really has bothered me, especially with old build systems, was I have written some massive ones in the past, and some of them I never want to return to if possible, because the build tools are just, they don't scale. So one thing we find with build tools, normally they work very well in a certain environment. Especially people tend to write a build tool for a new language they've developed. And then it works maybe very well in that contained environment, but as soon as you want to scale out of that environment, like started deploying things, putting things in containers, doing polyglot development, it doesn't really work. So what I'm really looking for in terms of build tools today, of the modern build tool, is quite a number of things, but two of them is, one, I want to be able to build irrespective of the kind of languages I use. The second thing is I want to install as minimal tools as possible, because another problem that you will find is that people will say, well, yes, you're going to develop with C++, argument's sake, but now this project uses CMake, now you have to go install CMake. Or you're going to develop with Rust, and now they say you have to install the Rust compiler, which comes with cargo. Or it just starts expanding. You have more and more tools that you have to put in, and now you have to control the versions. So this is the other problem. So you don't necessarily know the person who's going to build it, whether they have the right version of that. So what I like is, for a build system, is to be able to bootstrap as much as possible locally. So I want to go to the repo, check it out, run a bootstrap, and it should pull all of the tools in for me and make it available in my build system. It's the same problem on CI, because you end up in CI having to install tools. And then you get up having to, typically on Traverse, GitLab, you end up fiddling with scripts to put things in at the beginning. Or you're fiddling with Docker containers to put things in there. And once you get onto multi-platform builds, it even gets worse, because it just multiplies. So what I'm looking for really is a build tool that can actually provide me all of that benefits and then still somehow actually integrate with whatever kind of projects I am doing. And this is one of the reasons why I actually currently do like Gradle a lot, because it can actually, Gradle can do that. Some of the things it can't. I mean, every tool has its limitations. So I'd like to show you some examples where we can do with C++, we can do some Rust. I'll tell you some about other languages as well, at which state it is. And also show you how you can actually integrate with some tools, and once again where some limitations are in that respect. So what I'm actually going to do right from the beginning is I'm going to kick off and show you a basic C++ build. Okay. Sometimes it'll just disappear in here because it's very difficult to actually otherwise type here and have a look. Okay. So what we're going to fire up, and actually, I assume everybody can see the console properly up there. So what if we just do this? There we go. Can you read that, Jim? Okay, we can try put it into. Sorry?
Sorry, am I the designated blind person?
No, but you're pretty much sitting in the last row, or second last row, but you're paying attention, so that's why. That's why I'm asking. Okay.
Let's fix this the easy way.
Oh, okay. Right. Can you read that?
Right. That's great.
Okay, cool. Okay. Right. So what I'm actually going to do is I'm going to build a very, very simple little program. Let's get my mouse up here. And we look at the C++ code first. Okay. All of the code I'm actually going to use are all pretty much, the code's trivial because I don't want to actually focus on the code. I want to focus on actually the kind of things that you want to build. So that's a pretty standard little Hello World program. There's nothing fancy about that. Now, if you're going to build stuff with Gradle, it tends to follow this thing we call convention over configuration. So you expect source code to be in a certain location, and it assumes quite a number of defaults. Now, with Gradle, you can actually change this if you actually migrate a project, but I'm going to start off with actually following the convention. So the first thing you find down here is that there is, in your project is source, hello, CPP. So all of your source code actually goes into the CPP folder. Let's go there. This might be easier if I do this. Right, so that's my layout of my whole basic C++ project. I have a build script, which is called build with Gradle. You can ignore the settings of Gradle for now. In this case, it's actually empty. But that's actually all I had to do is dump my basic C++ code into. Now, let's go back to that code. If you actually look at the build with Gradle script, that's all I actually have to do. So the first thing we're going to say, because Gradle is based on a plugin system, so it has a very, very limited set of functionality. And then you say, I want to have this functionality, and you apply plugins for that, which is great. It means, firstly, your project isn't, or your build isn't actually lumped with a whole bunch of things you don't need. The second thing actually allows you to do customized sub-projects in a bigger project, which actually only focuses on specific languages, for instance. So this is what we're going to say. We're going to say plugins ID is CPP. And the next thing is, it's got a bit of a DSL I don't really like for the native stuff, but that's the way it goes currently. This will actually be improved. It's basically it's a model, and then we say we're going to build components. You can have more than one component, but in this case, I'm just going to say I want to build an executable, and you have to use a special keyword called native executable spec. And then in front of it, there's the word hello, and hello is actually that's the name of my specification, and by convention, it's also going to become the name of my executable. So that's my first C++ project. So with that applied, there's another thing that you should actually do in Gradle projects. It's called the wrapper. I think it's this directory. Yes. So at the top level of your project, you would normally apply the Gradle wrapper, which is the first bootstrap you can actually get. So instead of actually installing Gradle, you create this wrapper and you put it into your source repository. So when I come along, all I have to type is pretty much Gradle W and kick off the project, something like build. It will then actually go off and bootstrap Gradle for me and put it at a safe location. It won't put it into the system location, it's on a per user basis. So the first good thing there is I can just tell you go to this repo and run build. Actually, I can tell you go to my repo for this presentation, pull it out, and just run the script Gradle W build. And it will actually bootstrap everything you need. So already actually basically eliminated one thing. So I eliminated the need for somebody to install a specific version of the build tool. Now, that's what I'm normally going to run. I just have an alias on mine so I can type it quicker. So I'm just going to show you the first thing is, I've applied that plugin. Let's look at what tasks are available, because we're going to build an application called Hello. So Gradle runs off, and now what you will immediately see here is we have a compile task, and we have a link task, and notice it actually says compile Hello. That's the name of my project, and then it just creates an executable, and it will also have a link task here. And if we go a bit higher up on this, it also has a task up here, which is hello executable. That's all that I normally have to run, and it will then build the executable by name. So if I have two executables I want to build in the same project, it will create two names in there. It also has a second one in here called install, which allows you to take all of the dependent libraries it's got, plus the executable, and it puts it in a directory which you can then zip up. It's got a number of other ones, it doesn't really matter, but so let's just try and build this. And I can actually run a shortcut just to say build. That's a life cycle task. So most projects will have a build in it, so I can do that, and it will actually do the other ones. And yes, to prove my point, I will run that. Now you will actually see it run. You can see it ran the compile task, it ran a link task, and then it actually done this task. But this task is actually dependent on the task doing the real work, which is compile and link. Can you see from that side? Let's see if we can move this. Otherwise you have to move that side. Good, better? Okay. Right. So basically, Gradle works out the dependency graph. So, and that's one of its strengths. It's really good at working out these dependency graphs. And it will make sure there are no cyclic dependencies as well. So you can't have one task depend on another one, which depend on the original one. It will work that out at evaluation time. So that's basically the task it just gone through. It will give you different states as well. So it has a check task in the life cycle which run the tests, but it will tell you it's up to date in this case because I have not declared any tests for this project. And it's just gone through that. Now you've noticed there's very, very little output. The output actually appears now, and we can see where it is. We'll run tree again. Now look at how it's changed. We had our builder Gradle settings in our source code here. So by default it always creates a directory called build. You can override it in Gradle, but very few cases where you would. And then it's created the exe folder because you want to build the executable, and it's dumped the hello executable in there. It creates a folder for creating all of the objects in. Once again, notice how it matches the name the whole time. It calls this hello CPP because we were actually building C++ source for the hello project. Then you find this folder in there. It's a kind of a hash that Gradle works out, but it's not dependent on the files you actually build, it's dependent on the project. And the reason it does that is because you start building multiple platform stuff. It actually wants to find a unique way of caching these things, as well as you can have, in the latest version of Gradle, you have this build cache where you can actually cache artifacts between different people's machines. So you can have like your CI run, do a whole build, and it push the whole cache out. So if you come in and work in the morning and you start off, it will actually collect the files from that cache, so you don't have to rebuild everything. And you can implement your own build cache as well if you want, but there is the Gradle company actually, they offer a build cache, and there are some open source versions as well that's now implemented. Yes.
Sorry, could you expand a bit on the multi-target stuff? Because at the moment I'm building on an NFS drive,
yeah,
but I'm building it from different systems. And I'm using AutoTools and I'm hand creating a build directory and I'm configuring the build directory. So you're saying that
it deals with that on NFS.
Yeah.
Yeah.
I haven't figured out how it deals with it at the moment.
Well, I can't get into that detail because I actually don't know myself. I'll have to look in the code for that.
All right, okay, all right.
I've used the hashing kind of thing a couple of times for different things as well, but all I say at this point to know, you just have to know there is an intermediate folder in here. Okay. And I think that is actually probably to do with the machine as well. So. And okay, so the other part that you have to know in here is if you want to find the output, because if your build fails, it's just going to tell you it failed, but it doesn't going to give you much detail. So for both the compile phase and the link phase, it will give you the output of the compiler and linker. It always put options.txt in there. So that's actually what gets passed to the compiler or the linker. So let's have a look. Let's look at the compile. Good. So if you're familiar with C++ compilation, this wouldn't be unfamiliar to you. So it actually writes everything into a file and then uses that typical thing you can do with most compilers is pass the options to it as a file. And one of the reasons it obviously does this is because certain compilers can't take a lot of parameters on a command line. Okay, so you can actually go and see, this is actually really nice, because you can, at your own leisure after the time, go and actually see what was passed, instead of trying to scroll through a backstroll, trying to figure out what was on the command line. So that is pretty much the basics of how you can start off with a C++ thing. So obviously I'm going to tell you this trivial in the sense that the program I've just done is trivial. Your progress will grow, so it will be more complex than that. But the point here is to actually get you started off. So we go back to that, and as I said, that is pretty much it. So let's swap this around. Let's actually try to build a library. And I'm going to go through these things. Each of these steps with little examples we use gets a bit more and more complex. But it's good to actually get the basics under these, so you can, if you get to the next one, it doesn't look that complex. Okay, we're going to close that. Let's look at building a library. Okay, we're going to pop that up, and I'm going to pop it back here first. Right. Going to run tree first, and you can see pretty much what we're going to do this time is I'm going to build a little library which we're going to reuse. It's just a simple print line library. You give it a piece of text, it prints a line, and it puts a carriage return at the end. But with a library, you normally have headers as well. So this comes to the Gradle convention. Normally here you would put a CPP folder, put a source in there, and all headers that you want to export, you put in a headers folder. Now, if you're used to a classic way of developing C++, it might sound a bit foreign to you. And feel sort of, I'm not so sure. But it has its advantage of doing that way as well, because it clearly separates what header files has to go with a library if you ship it and what you can use internally. It also prevents you generally from accidentally not shipping a library or a header for a library. Now, let's look at the code. Down. Once again, the library is pretty simple. I am just going to create a standard library which you can either give it a stream or a piece of text, and it will print whatever you give to that. Obviously the code itself is trivial. Okay, so we're going to go to the build file for this, which is more important. Now, previously, actually, in the previous one, we had native executable spec. Now we say native library spec. And once again, we give it a name. So I gave the project print line. By the way, don't worry about those things. I leave the comments in there because they actually, if you look at the documentation, you will see there are all sorts of things. If we pull the documentation across for a moment. You will notice these little numbers in the documentation. That's just a way with ASCII Doctor, which you can actually link comments and code to the documentation. So if you want to pull this afterwards, you'll actually find lots of comments, which explains lots of these little lines as well. So if you can't remember anything, as you said today, even after the exercise, of course, you fell asleep, you can always go in and read that. Okay, that's all we have to do. We still have the C++ program, and we're actually going to build it. Okay, I'm going to run my tasks again because it has now slightly changed. Because obviously if we build a library, we have a choice between building a static library and a shared library or dynamic library. You will notice immediately on the compile levels, we have two compiles, one for building object modules for shared and one for static. Now, once again, all projects I work with never did that, but this gives you a very good chance to actually optimize object modules depending on where they go into an archive or into a dynamic library. You'll find a normal link task in there for linking dynamic libraries, and for creating archives, static libraries, it's actually called create. And once again on the top, you will just find there a thing called printline, shared library, and printline static library, which is basically the entry task for building either static or dynamic library. But once again, if I just go and I say build, it will do both of them. So let's run that. Actually, let's do that. By the way, the other thing you'll notice, the startup time is very, very fast. It just builds like this, because by default nowadays, Gradle runs as a daemon. If you're familiar with Java code, normally you know there's a penalty for startup. So effectively, the first time you fire it up, it fires up as a daemon, and it just keeps it there running. And it actually caches a lot of your build code as well. So you can actually quickly decide what to rebuild. Even though I've actually cleaned this, because I've cleaned all of the projects before this, you can actually see how pretty fast it actually went through this. And this is just a plain old MacBook Air. Anyway, so you can actually see the phases it went through. We want to build a shared library. At some stage you had to link it, but before you could link it, it actually had to compile it. You'll actually find something interesting here is that it did a shared one there, and the shared one there, and then the static ones in between. The reason for this is two things. It actually works out what the dependency tree is, and if there's no dependencies, effectively the rest of the tasks that remain just gets executed in alphabetical order. The Gradle guys will tell you don't rely on that, but I'm just telling you that's actually what happens, because that's how their sort works. So that's why you actually see the things, not necessarily what you would thought is in that order, but it's a complete logical order to do it. So the same thing we had to create static library there, and we had to create the compilation for the static there. So you've got everything created. And if you now look at the tree, it's obviously going to be a bit bigger. But immediately you've got the same kind of things as being repeated here. For each of these tasks that get executed, like compilation and linkage, you will have the parameters get passed and the output. I just don't know if actually for what reason it doesn't actually produce options for a static, creating a static library. And then once again, you can see you have separate directories every time getting created for shared and static. The other reason for doing this is it allows caching to be much better, because it's harder to work out if files have changed in a single directory whether you want to cache the whole directory or not. So one reason to split is that besides actually have nice logical splits, you can actually, Gradle can cache it a lot better. Okay, questions? That's basically a library, and yes?
Can you add to the options?
Sorry?
Can you add to the options?
Yes.
And then it rebuilds with those options?
As we go through, there's an example that adds to the options. Yes?
The temporary directory names, the kind of hash names, make sense for the object code.
Yeah.
But I don't understand why it's not doing the same thing for the built libraries or the built executables. So if they helped kind of building for multiple configurations, if you're going to come to it, then don't worry, but I don't understand the
I don't either. It makes it easier to find it, that's all. If it's a temporary, but yes, I don't know actually if you're going to build it cross-platform on NFS, generally what's going to happen. Except if you build cross-platform on NFS and specify different platforms, it will actually create separate directories for each platform.
What's the reason you're using IntelliJ IDEA? Is it obviously it's a native code talk?
Okay, the reason because I use IntelliJ a lot.
I mean, does it work with C-line? That's another question I have.
Yes, exactly. But it has, well, the C-lines, Gradle support for C-line is still coming. I asked Phil about it. But I get a real Gradle support inside IntelliJ. And I just needed an editor to display things. I can do everything for you in VI if you want. It just gives you a bit better syntax highlighting, but that's the only reason.
Why does it compile twice when you could compile just once relocatable and then create either a shared library and a static library?
I think you can combine it. The reason is it allows you to optimize object models depending whether they are going to go into a shared library or a static library. And there's definitely libraries I've picked up on the net where things are different. We worked with one last year where certain things you would find in the static library but not in the dynamic library. Okay, cool. So we're going to look at the next one. So at this point, we actually pretty much built the library and an executable, but obviously you need to test these things at some stage. So we're actually going to look at one. I'm going to use Google Test for testing the code. And the reason why we're doing this is because it actually got built-in support in Gradle for Google Test and for CUnit. Unfortunately, the way that currently the Gradle code works internally, it's very, very hard to extend it in a nice way to add additional support for other testing libraries. Hopefully, by Gradle 5 comes, they would have sorted this problem, because when Gradle folks went off to develop the original software model for native, they had this grand vision, except that it wasn't really that user-friendly, and it's a very, very hard model to code against if you write a plugin. So much so that I think 3 years ago, they announced at the conference, so I felt vindicated after complaining about it for about a year. So it is changing, and hopefully in Gradle 5 to have a simpler model, and then it will be easier to add things like catch in there. Currently now it's a bit harder to do because you have to effectively wire everything in manually. But let's just have a look at a version where you can actually build it. So I'm pretty much going to have a library, still have my standard library, but I want to test it, so I'm going to create another folder called printline test to split the two apart. And there isn't really much in the test code, the standard Google test. It's not very interesting. But let's have a look at here. Now suddenly it's exploded. So let's have a look. We're going to go back to that section first. Oh, firstly, I am going to tell it, still doing C++ work, but I now want to use the Google test suite. And this is another thing that sort of irritates me, the fact that there's test in it twice. But okay, we'll live with that. You know, every family has got its own problems. Okay, so let's have a look here. So we still have components, print line, with school and native library spec. But what we're now going to say is add a set of test suites, which the Google Test plugin provides, and that what we give it a name. Well, obviously, you saw print line test is in there, and then it's called Google Test suite spec. Now, so we're going to say what we are testing, and then you have to use this strange syntax called $.components, which refers to that components, and then the print line library. Then you have to actually do extra things that you want, and you've asked about adding options. So we're going to say for all of our binaries, for instance, if it's Visual C++, we're going to add a DL export defined. The same thing, you can actually add a bunch of options as well. This is just a very quick intro here, you can do that. And you can configure this based upon all of the binaries in your project, or one binary that you want to compile. So you actually, if I have multiple libraries in here, and I only want to change for that library, I can actually put the binaries block inside there as well, and just configure the compiler options for that specific library. And then we have to put some extra things in here, because we have to now say, we have to use the Google Test library, which is external, and it doesn't get provided by the plugin. This is one of the problems we run into for native normally. And I want to tell it I want static linkage. So it's nicely described. There's no way of having to go, what's that keyword, what's that command line parameter again I have to use for static linkage? I just tell it linkage static. That's English, it's readable. And here's another example. If I'm building for Linux, then I want to, for instance, add pthread to it as a command line option. So there's your command line args. There's your linker args. Okay, that's fine. So the other thing is, where does it find Google test? So we have to go back to this block. So we have to find this block called repositories up there. And it's got a special thing called pre-built libraries. You have to use that keyword. And basically, this can be anything. We're going to call it Google test because it makes sense. It's called Google test. That name there, Google test, will actually match that name there. Otherwise, this won't know where to find the library. So that one actually matches that. And we are then going to add a couple of things there. We say for that library, where's the headers? And in this case, I'm just going to pick the headers out of an environment variable. And I'm going to say to find a static library, it's located somewhere there, and I've actually going to change, depending whether it's Windows or not, the name of the library. Okay, now, this might confuse you. I'm not going to really delve into that now, that little line. It's an interpolated string, and it's a Groovy feature. Now, one thing I didn't mention, so you saw the DSL. The DSL is actually a Groovy DSL. You also can do a Kotlin DSL for Gradle, so if you don't like to write your build script in Groovy, you actually write it in Kotlin. I prefer the Groovy version because it's much more mature, and I think it reads a lot easier. But effectively, all that will do is we'll look for a target platform operating system element and check if Windows is set to true, and then it can decide which name to use. If you want more details, I can actually give you details afterwards, or you can just go and read a bit about Gradle. Okay, but that's what I have to do. We go back to my build. And we're going to go to the tested one. Once again, my tree is pretty simple before I started. And my environment, for instance, contains a variable called Google test include. So that's why it's going to pick it up when it runs. It reads it from the environment. That I just made it a lot simpler for the time being. The problem here is, the first thing, I had to install Google test somewhere, get it compiled, etc. And then I have to tell my build system. Now you can know, if it's my local machine, it's going to be in one place. If I push this to CI, I have to ensure it's on CI as well in some form, and how is it going to get there? So that's a maintenance problem, but let's not worry about the maintenance problem yet. So if we look at our tasks now, because we've actually added a test suite, now you get some very, very long names. But that's pretty much print line test, Google test, and it actually compiles a source for your test suites and creates an executable, because Google test is effectively becomes an executable which you run and which creates you the results. And what I'm actually going to do, I'm not going to run the whole thing now. I'm just going to say, let's just run check. So it just runs the tests. Run that. It goes off and compiles. Now you see, obviously, I have nothing compiled yet. So it just says, well, the test program needs the original library to be compiled. So it went off and it actually compiled the code and then linked it. And then you can actually see this, not much difference there. And then it actually runs the test. And you can actually change it. You can pass command line parameters into Google test that actually produces your output in XML, etc. But it's as simple as really doing that, except that you have to manage this problem with external libraries. So I'm going to come back to that a bit later. So I just want to sit down for a moment. But that's one thing. What if you actually, we've built the library and we've built an executable. What if I want to build a whole application where I build libraries and then I might want to build an application which uses libraries. So I don't want to build one big fat project, because normally you have effectively a whole bunch of sub-projects in your big project. So what you can do with Gradle is what's called a multi-project library. And let's go and have a look at that. It gets a bit more complex, but it's actually, this is one of the great things about Gradle, because for instance, if you work with Make, you have to start defining something at top where you then just have to say, well, go through this thing and make minus C, yeah, make minus C, make minus C, and you have to put all this linkage between the sub-projects in manually. So we don't have to do that. Let's go look at a C++ multi-project. Actually, I'm going to swap over to my console first. Let's run the tree in there before we look at the files. So what I actually had, I want to build my Hello World application, but I want to use my println library to actually do the output. Now I have a subdirectory called Hello Application and a subdirectory called println library. And you will actually also notice that there's source and there's a builder Gradle in each of those. What I can actually do in my source is, let's start at top. Now the first thing Gradle wants to know is how many sub-projects do you have. So this is where the settings of Gradle comes in. So we create this and we say include Hello Application and include println library. Gradle now immediately knows it has to go into each of those folders and look for a builder Gradle file. Strictly, you don't even need to do that. It can actually run the sub-projects without builder Gradle files if you configure everything from the top, but that's not important at the moment. So all I've done in my top level builder Gradle, I just said declare a version, and I use this word all projects. That means that it's going to apply the text of the configuration. Version is 1.0 in each of the sub-projects, which is Hello and println library. And if I go into my library, the code's still pretty much the same. And this will change now, however. Now my Hello application has to know about the library. And for instance, if I build my Hello application and the library isn't built, it has to go off and build that. So this is what we're actually going to do. So I've actually done a couple of things here. Firstly, I've applied the C++ plugin as usual. We'll come back to the distribution one. It's actually got nothing to do with that building. It's just a separate thing if you want to do. What I said, when I build my executable spec, I want to rely on a library. And I've now actually extended this little block to say I'm declaring additional sources that my application depends on. And all I have to say is this line, project, println library. And immediately it can link to the other sub-project. And I want to say I'm interested in the println library that gets created by that project. So ignoring the zips for the moment, all I have to do, and this is the one thing you can do in Gradle, you can actually do this in more than one way. You probably know if you like work with a Make project, you can go into a directory and obviously build from there. Or if you build from the top, you have to say make minus C. So in Gradle, you can do similar kind of things, but you don't have to tell it to go down to another directory because it builds you a whole model. And let's look at what this has built for us. You will now actually notice there's a whole bunch of tasks here that gets prefixed with colon and a name. So you can run any task in any sub-project from the top by just specifying the project name and the task name. Or you can change it to the directory and just run it by the task name. So what I'm going to do is I'm actually going to build my Hello application. Okay, it's misspelled. We'll fix that. So I could have just run build from the top, but I actually want to explicitly show you. So I can run that one specifically, and it will actually go into the other sub-project and build it. So you can say started, that's empty, so it's going to ignore that. So we actually go down to the bottom. That was the task I specified, and it's now going through this, and it says, well, I want to run Hello executable, or I want to build this, and then it realizes, hold on, it needs these other tasks, so it's going to run them first. So it actually builds the println library first. The interesting thing here is it actually compiled the source code first. Then it actually built the library because it already knows where the header files are. But in order to link, it has to go off and build the other source code in the library. So it works out a quite smart path through the whole code tree. And effectively, that's what you had, and we can actually run this. it's ran install, so I can go and run that. Oops. Now I have to go into my subdirectory, hello application build. We ran install, so we have this little app there, and we can run it. We'll say usage, and then we can just say hello ACCU. So it's pretty much relatively simple. Well, it's built in a very, very simplistic way, but it tends to put things in specific directories, so you normally would expect to find them. So you'll normally find your build reports will be in the reports folder. You know, your executors should be in an exe folder, and aptly named below that. Now, I want to get back to the distributions one for a moment, which is all fine and well to build this, but let's actually want to zip this up or tar this up and send this away. So we're going to go back there. So that's why I've actually applied another plugin called distribution. Distribution provides all of the tasks to actually tar your files, zip them, etc. The only thing I had to do is put this little piece of code in there, because what I want to say is, from that install hello executable, I want to take all of its artifacts. So I say for my zip task, my tar task, and my install task, grab everything that that task produces, and then put it in the zip. So it's already actually built a zip because I said build, so you can actually go and have a look inside there. So you'll actually see it's created a tar file and a zip file. You can compress the tar file as a parameter that you can pass, but effectively we've got that whole thing lined up in there, and if I grab that, you see it's actually packaged the whole thing inside there with the appropriate dynamic library as well. So it's very easy to actually orchestrate all of these sub-projects together, and it's actually very little effort. And as long as you're building pure native with the built-in support, you can easily link projects together. So you can very easily modularize your code into separate libraries and just link them into main applications. Okay. What time is it? Okay. So we have to finish at 4. We've got 40 minutes. That's good. Okay. Questions at this point? Yes? No, not at all. I just added it in there as an extra thing. Yeah.
Okay.
Yeah. It's got nothing to do with multi-project at all. You can put anything into multi-projects.
Suppose your code depended on a third-party shared library.
Yes.
How would you include that in your distribution?
It should pick it up if you specified it in the same way. If we go back to the code, it wants to know where, of course you want to package it as well, right? Yeah. There's more than one way to do this. The one thing, if we go back to our original project we did with the testing, right, I just want to pull that up. If you have this kind of linkage where you specify the library and knows with, it could potentially pick this up. If for some reason it doesn't, because there are several cases where it won't, you can simply just go back, and I could do something like, sorry, it's that one. I said pick that one up from there. Let's just say I want to pick another one up from I don't even know. It could be in your project, or it could be anywhere else. Actually, you could just have that. You can effectively just specify a path, and it will pick that up as well. You can have something like that as well. Libs. And you can say only include in that directory libraries that start with exported arguments, sake. Something like that. And it will only filter those one out. Those are AND filters. So if you actually know a little bit of AND, then understanding the filters are easy, but they are pretty well self-explanatory. Yes?
But most probably, if I'm depending on a third-party library, I want to link to it as well,
Yes.
independent of whether or not I want to ship it with the distribution.
Yes.
But basically, at this point, I could refer to that target that I've presumably built somewhere for
Yeah.
linking, so it will figure out the file name from that target. Right?
Pre-built libraries, it shouldn't necessarily always pick up and put in distribution. But if you declare something as pre-built, it will put the linkage path in, but it won't necessarily pull it in.
I'm basically getting at, instead of writing .so
Yeah.
in order to be platform
Yes.
independent, I don't want to
Oh,
type
okay.
file name because my .bdylib or .a, .so,
That's right.
whatever, or DLL, and I don't want to type it here.
Okay.
So I want to define an abstract target and then use that
You mean
wherever possible.
if you just want to include a file in itself, not that, because this one takes care of that, because that's just the base name.
Right, but that one we build ourselves
Yes.
as a dependent project.
Now you want to depend, okay, so we go back to this one again firstly. So in this case, I actually had to specify because the names were different, right? So there are different ways of declaring that. Sometimes you can just declare the base name and it would work it out depending on the platform. But because I actually use this construct, you have to specify the physical name. But there is also a way of actually working that out. There is a construct in Gradle which you can just say, give me the extension for a dynamic library, and it will give you the correct extension. There's a way that actually you can give it the base name and it calculates the full name. If you ask me now, I can't remember. I'll have to look it up, but I know it's there. Okay, so that was our build, and we have actually built that, packaged it up, and we have some questions. So let's have a look what we can do as well. So we've done you can actually see that you've done C++ libraries, C executables, well, C++ executables, and you've actually build a multi-project where you can link them together, etc. So what about working with C code? So let's look at a library, but actually I'm not just going to work with C code because it's effectively a rehash of what we've just done. What I want to do is I want to build a project where I mix C and C++ code in the same project. Because I don't know if it's really that common anymore, but I know I've worked on projects where that gets done, so let's have a look. We are going to go to this project. I'm going to show you the tree of the project first because that's easier. We're going to build another Hello World application, but this time I'm actually going to do the print line implemented in C, and I'm going to call it from C++, but I'm going to mix all of its source in the same folder. You know, notice I got my header file inside here as well now. I don't want to export that header file because it's part of my application. All right, so let's have a look at the code. Well, we saw this code, so I don't really have to go through that again. Let's just look at the build file. Okay, because I'm building C++ and C, I have to actually add the C plugin as well. And the rest is, to some extent, the same. We're going to say, I want to build an executable. Well, once again, I'm going to say native executable spec. But now, because my code is mixed, I actually have to pick out C++ and C bits from that folder. So I'm going to explicitly specify to it where to find the C code and where to find C++ code. And this is one of the kind of things where I said it follows conventions, but if you want to have a different layout, you can. All you have to do is start using this source dir keyword and include what you want. So you can, for instance, only say source dirs, and it will always just by default include either C or the C++. But I explicitly called it out here. I'm going to work in that source directory, only pick out anything down the tree that's ends in C, and here obviously everything that ends in CPP. Notice I didn't care about the headers. It works out the headers in this case. And we can actually look at what tasks we have. I know I carry on looking at the tasks because I think this is quite important because these names get very, very long, but you can actually see how it matches up with names. Important here, firstly, it's created a compilation task for both C code and C++ code. It doesn't try to compile them as one. This is what we normally do anyway. And obviously only one link task, because then you go to the object modules. The rest actually is still the same from the previous cases. We still only have one hello executable because effectively we're only building one application, irrespective of how many compilation tasks we have. And that will give that to you, and you can actually build it. See what order it actually goes in. Once again, since these don't depend on each other, they could have gone both either order, but you can actually see the little alphabetical ordering that went on there between those two. And obviously, it can only link once it's done all of the compilation, so that's what a link task is there. And these are pretty much just lifecycle tasks. This is the one I wanted, and it's built my hello application. So this is actually relatively easy to mix the two. Okay. Now, that's all fine because you're working inside the same project and just using the native stuff, but you are going to typically end up having to use other stuff. So we're talking about external tools like you might have a part of your code is still being built with Make, and you have to build it with Make. You have to use CMake, for instance. You might want to pull things and we're using Conan. And you have a couple of other kind of things you might do as well. Those are just examples. So there is actually integration between Make and Gradle today. So you can actually point it at a directory where there's a Make script in it, and you can actually also just declare inputs and outputs, which you know the file depends on, and it will actually go off and run it. You just give it the targets and it builds it, which is quite useful. The problems you have is currently we have no integration directly with CMake. If you want to use CMake, you effectively have to run what's called an exec task, which effectively calls out, and you either have to tell it the path to CMake, or you have to assume it's on the system search path. And I'm actually going to run an example of that before I talk about Conan. So let's grab this project. There we go. Now, you remember earlier I had the example of pulling in Google Test from the environment, and I didn't want to install it. So what I'm actually going to do now is compile Google Test as part of my project in a cross-platform way, and then use that to test my printline library. So the first thing we're actually going to do, there's nothing. You'll notice there's a Google Test folder, but only a build a Gradle file in there. And obviously here I have my normal kind of code, there's nothing else. So let's have a look at what I've done there. And this might get a bit hairy, so we're going to run this from the top. When I'm going to start first, the first thing I want to do is actually I want to download the source code in my compilation time. So I've applied a plugin up there called VFS, and I'm going to use that to do my downloading. And now what I have is I'm going to create a task which is called fetch, and you can create arbitrary tasks in in Gradle. And you can put any action, you put any action in a do last, what you actually wanted to do. So I've just defined a couple of variables up here, and you normally would do this in an ext block in Gradle. So I'm going to say where the URL is to find Google Test source, and I also want to tell it to collect it from a specific branch. So there's the master branch, so I can pretty much just do an HTTP GET on that. And this is what we actually do in here. We are going to say copy that archive you can get from GitHub, because there's normally a button you can click on GitHub and say download this branch as or up to this commit as an archive. So this is effectively what we do. We just pass it that. but we'll also put zip in front of here. This is pretty smart because what it will do now is we'll actually download that whole zip and unpack it on the fly. So you don't have to have a separate task to unpack it. So it does it in one go. So we've downloaded the source, and now we actually have to build it. Now, because the first step of building Google Test is to actually call CMake, and I don't have CMake elsewhere, so I actually haven't installed on my machine. So I'm just going to say run CMake. I create this thing, which is an exec task. Okay. Other thing I just do is I don't want all of the CMake output cluttering my screen, so I just killed it off by putting it in a stream. And that actually allows us to build or create the appropriate files. And now we actually do something which is pretty hairy. But basically, it's an if statement that says if we're building on Windows, we're going to apply the MS Build plugin. If we are building anywhere else, we're going to apply the GNU Make plugin. And I'm just going to stick to this bottom part now. So I've just declared some variables because I know where the include directory is going to come from, where the lib directory is going to be after it's built. And pretty much that's all I had to do. I had to tell it which directory to change into, because I have to change a number of directories down once I've pulled it and unpacked it and CMake has run before it actually can build it. And then the one thing I've put in here is because it's a make task, this is a special Google, it's a special Gradle construct. I can say anytime I see the make file changes, rebuild or rerun this task. Or I can tell it if I see that lib name is missing, I know I have to build it. So we can actually explicitly declare statements like that as well. So now I've actually can build my Google Test library. What I have to do in my print line library now is much of the same, except we don't have that ugly statements from earlier where we had the environmental variables. I pretty much declare two variables up here, which is my include directory, which says go to this project, look at this task, and pick that variable from there, which is those variables I've declared up there, or there in case of Windows. So it knows where to pick them up, and we effectively just converted the file objects here. That's what the purposes of a file statement in Gradle. And I can tell it where the source there is and where the library is. And the rest is effectively the same. The only other nasty thing I have to do, and this is because of the way the software model was written, I still have to explicitly go and declare a dependency. So I'm going to say for anything in this project, which is C++ compile task, make sure that the Google Test, assembled Google Test project task has run first. So I created depends on relationship. So let's run this. I'm going to run it from, actually, let's just run it from, no, we can do a different scenario here. We're actually going to change to my print line library as if I'm actually doing a lot of work in that library. Am I in the right? Oh, sorry, I'm in the wrong folder. Okay, so I am changing to, and now I'm just going to run tasks in here. You will actually, because this is a multi-project build as well, this now only lists the specific tasks in this project, so it doesn't actually refer to the original Google tasks, Google Test building, but you'll see if it runs, it will actually build it. You can see it goes off, it fetches it. You get some cookie rejects from GitHub, but that's normal. Now, let's run it up there a bit. But you can see I have success. So far, all of my live demos have worked. Okay, so that pretty much runs the CMake tasks. That has done the download. And now it's actually done the assembly, and it's done everything, and it's actually run my tests as well. So that's building Google Tests, building the library, running the tests. So now actually I can check this into CI, or into source control. CI can run it. It will actually bootstrap Google Test itself. So I don't have to do extra work. Anybody can pull it down. They don't have to worry where it comes from. So that's one way you can actually bootstrap. The thing here which we really need is you really need to be able to do this for Conan. The problem is there's no integration between Conan and Gradle at the moment. And it's painful. Yes, we have to fix it. And if that's there and it integrates, of course, Gradle's got very, very excellent dependency management. If you can get that integration, you should just be able to specify what you need, either via some parameters passed to Conan or just nice couple of statements, DSL statements in Gradle, and it then can actually farm out to Conan. The other problem with Conan that I have at the moment is that it's actually written in Python, and the best way to install it is to use pip, which means it's more work to bootstrap it. If I don't want to install it, and I want Gradle to bootstrap everything, I can't. So I have to have that installed on my machine. So we have that kind of problem there currently. That it might not be the same version or something. I also have to bootstrap. I can't just bootstrap it on CI as well. I have to effectively go onto my setup scripts and fiddle and do a pip install before it runs. Or I have to create a Docker image which has it already installed. So yes, you can do things, but it is more work. And it's both more work to maintain it in CI, it's more work for developers. I can say I hate it when I have to go to a project and people say you have to install this and this and this. It really gets me. It wastes a lot of time. But that's pretty much, actually, we've integrated a whole bunch of things. So we have not 20 minutes, it's good. So we talked about C and C++ a lot. I am going to talk about building Rust from Gradle. Yes?
Before we build that,
okay.
You say that you have the C++, but you don't specify which C++ compiler you use.
Oh, yes, before we go to Rust, let's talk about that. Okay, right. Let's pull up a file, let's close that. I forgot about that. I'm not actually going to run this full project, but I am going to pull the build Gradle file and talk about this. So, by default, Gradle has some things. It will know if it runs on Linux, it's going to look for GCC first. If it runs on Mac, it's going to look for Clang first. If it runs on Windows, it's going to look for Visual Studio first. Okay. It knows that. You can change that. You can also tell it to use a different tool chain, etc. It's very, very configurable. So let's go through a couple of things. This is a kind of things that you can do when building native code with Gradle. Firstly, it's got a thing called build types. You can specify anything in build types, but I mean to do debug and release is quite common. Okay. You can also have another thing which is called flavors. So flavors sort of things on the side. So build types is much more functional. Flavors can be anything. So for instance, you want to release a community and an enterprise version of your product. You can put two flavors in there. And you can then later query that and make decisions based upon, for instance, which build type it is or what flavor. And you can do all sorts of other things. So for instance, I can say for my tool chains, and these are default names, but it's of that type. So you can put any names in here. For instance, I can put in like say GCC 4 and GCC 5. And then you can specify where to find it on the system. And there's a couple of other things you can figure out, but you can actually configure your tool chains quite well. What I've done with one of the GCC ones at a customer is they build everything in a cheroot. So I effectively changed the GCC tool chain to call the cheroot and then invoke GCC in the cheroot. And you don't even notice it, but just because the toolchain definition is that everything just worked. So you can do things like that. You can actually stick scripts in the middle to do something else first before it calls the compiler. You can specify things for platforms, and once again you can have different names in here, but you have to, these are fixed names, but these ones can be anything. So I have max, I say if the architecture is actually x86-64, call it AMD64, just for today's exercise. Now, what you can do with this is, for instance, I have the library I want to build, but I only want to build this library if my target platform is 64-bit. So you can do things like that. So you can have a massive definition and only build certain targets for certain platforms if you want. I can also, for instance, say, for instance, of my flavors, I want to build for enterprise, add a define in there. I mean, it's quite endless what you can really do, but you suddenly have all of these options. Obviously, your script is going to grow. The great thing is about it, we can pretty much debug this, so which you can't do with Make. And so we've done a couple of other things. Now, for instance, we say if it's debug and it's GCC, pass -G. Obviously, if it's debug and it's Visual Studio, pass all that parameters, etc. So you have all of that kind of things that you can do. Yes.
Do I need to specify these compiler arguments in the Gradle file that is part of the repository?
What do you mean, part of the
So
repository?
you put now the definition of debug means pass -g to GCC.
Yeah.
I don't want to do this. I want my build system to do this for me because it knows what the debug build is. Because now I'm ending up having this option in all of my projects and I basically only support that compiler usually, or compiler flavor.
How would you do it in another build tool?
For example,
I see.
bjam,
Yeah.
you specify, you use a config in your home directory, you specify my GCC lives at that location, takes these arguments, is configured that way, and then the file in the project doesn't even know about this. So you invoke your tool, and we'll pick up your default compiler from your settings that's outside of the repository and just
Right. Okay.
do this for you.
You can do that.
And even in that specification, I'm not specifying what a debug build is to the compiler,
Yeah.
because that's built into the bjam tool itself. It has built-in knowledge about a debug build means I'm going to ask the compiler for debug symbols,
Yes.
which is -g on GCC, and is these other options on Visual Studio. So I don't need to repeat that information across all my projects.
You can, okay, I'm going to have to answer this in 3 ways. The first thing is, by default, I think today Gradle does not do that. Secondly is, yes, you can, what you explained, you can put a configuration in your own Gradle properties file and you can pick that up. The best thing, and of course Gradle doesn't support enough, is actually, if you know this kind of thing, to have an additional plugin which puts all of those things in automatically, so somebody doesn't have to do that. It's actually a good feature that can be added, frankly, just to make simple.
What
Yeah,
I'm
yeah.
missing.
Yeah.
And same thing for threading. You put the pthreads explicitly
Yeah.
in your Gradle file.
Yeah.
I don't want to do this because I don't know what the option is on whatever target I'm
Yeah.
compiling for.
I'm not actually sure that that's necessary in that case, but you are right in the sense that you don't really want to do that. But now that it just shows the example, you could pass things in from the build script.
Sure.
Yeah.
Like all tools do
Yeah.
this.
Yeah.
But this
Oh, that's a good point.
This is the reason why I don't consider Make to be a build system. Make is a tool to write your build system in, but it's not a build system.
Okay.
And this here basically now looks the same. And that really puts me off using this.
Okay. I think that's a very, very good point. Yes. Andrew.
I like the way that you showed how you can run your Google test after the compiler link.
Yeah.
How could you get it to run Doxygen after you've done the...
Yes. I was going to put an example and I just realized I was never going to have time for that. There's a Doxygen plugin. You just apply the Doxygen plugin and then, do you want the Doxygen to run after you've done a code or during any phase?
You want to run after, and if there's a fault with the Doxygen, like you've said, trigger an error if you fail to document something,
Yeah.
then you want the build to fail.
Yes, it will happen.
And another thing, suppose everything works, what about digitally signing your executables at the end as a post-build step?
Okay. That's not a manual step. There is a signing task, but I'm not sure whether it just applies to jars. But it's very easy to create a signing task, and we've done it for some projects.
Because in our Visual Studio environment, we have that built into our MS build.
Yeah.
If we were going to replace it with Gradle, we
Yeah.
would need to be able to do that.
You see, those kind of things are very, very useful things to know, because that's one of the reasons why you might make the choice to do it or not to do it. The wonderful thing about Gradle is you can actually write a plugin to just do that, and you can just release it, and other people can make use of it. Yes? Oh, that was okay.
Similar sort of our platform requirements, we would need to build a Windows installer and a kind of Mac app bundle.
Yeah.
Have you had experience with that, or other plugins for that?
I've always stayed away from Windows installers, but yes, I assume you build it with MS Build installer.
We use Inno Setup, actually.
Yeah. There's no direct support. So you're either going to do it via creating an exec task which calls a tool. You can use the MS Build plugin if you need to do that, for instance, and which will still invoke MS Build, but you can reasonably assume that MS Build will be installed on a development platform. That's pretty much it. You can always, there's a plugins.gradle.org which lists all of the plugins. You just go and search, you know, type something in and see if there is support for it. But that's generally what people would do, is write a plugin after a while.
I did a quick search there for the one that makes the Mac installer package.
Yeah.
And it has Java as a dependency, which I have a similar reaction to the one that you have.
Yes. Actually, I'm just going to, sorry, I was gonna answer your question. There is a tool, if you, but I don't know if you're up to date it's on Windows, but there's a tool called SDK Man, which you can install manual Javas in your own home directory. And there's supposed to be one called GVM or something, which runs in PowerShell. So hopefully that works, I don't know. But now that you can get Bash on Windows 10, you should be able to run SDK Man directly. Okay.
Yeah, another point on the build order. You mentioned that before, that on the multi-project build,
Yeah.
compiled all the things before going to linking the things.
I just said the order might look odd because you wouldn't expect it to be that way, but the order is still logical and correct.
So is there any way to influence this, or does it work out any other order?
No, as I said, pretty much the ordering is work out a task graph first, where there are definite dependencies, and do that order. And then look at anything else where there is no specific ordering specified, and then it just grabs it in an order that they have been defined or something like that. The other thing is if you specify it in an order on a command line, it will execute it in that order as well, unless there's dependencies between that. Yes, you can create specific ordering. You can say this task depends on that one, or you can say this task must run after that one, and things like that.
So how does it, I guess it does these things in parallel and uses multiple cores for that?
It can, but it will still work it out correctly. And it will err on the side of safety. If it decides it cannot run two tasks in parallel in two different projects, it won't.
Okay, one point I'm getting at is BGen, for example, knows that linking and compiling are two different things.
Yeah.
But one is CPU bound, the other one is IO bound. So it wouldn't execute multiple linking tasks at once because that's probably not going to make it faster. But if you defer all the linking
Yeah.
to after the compiling,
Yeah.
then you've built a serialized chain of things to wait for.
That's a
You
good.
can do linking while compiling other stuff.
That's a good point.
So
I
you want to do the linking as early as possible.
Yeah, that's a good point. I bet you Gradle can't do that at the moment.
I figured that you could do linking in parallel.
Yeah.
Maybe, depending on your system, you might run out of RAM because some link jobs can take gigabytes of RAM,
Mm.
and then your build fails
Yeah.
because of that. So it would be good to somehow have influence or a better default for these native tasks.
That's very, very, actually, damn good feedback. Thanks. I can go complain on the Gradle forum about this. Okay. Let's see if we have some time. Okay, we have 10 minutes. Let's play with Rust quickly. See if I can get everything through. So I'm going to pop through this pretty quickly. But I have some Rust things here, so I'm just going to do two projects. Actually, I'm going to fire off this one. So I have a basic Rust application. It's once again hello world. We're doing hello worlds the whole time. And that's a basic Rust that says hello world. I'm going to say I'm not actually a Rust developer, so my code is pretty bad. So Gradle's integration with Rust is still pretty new, but it does two things. It allows you either to do it by Gradle convention or by cargo convention. So in the Gradle convention, it uses source main Rust, and it's going to do source test Rust for the test code and source benches Rust for the bench code. It then works it out. The other thing is, in that mode, you don't have to have a TOML file when you build Rust this way. It generates a TOML file and then passes it to cargo. It also bootstraps cargo, so you don't have to install cargo or Rust. So you can tell it to find it on this file system, but you can explicitly say, I want to use this version, and it will bootstrap it. And I'll show you that. And yeah, let's start with this first. So here's my build Gradle file. I am going to apply a Rust plugin to build an executable. And that's the version, and I am specifying the version of my Rust application. Except you always have to specify it in Rust with the 3 numbers. That's a little catch. Gradle doesn't fix that for you, the build just fails. But that's pretty much it, and I can run that. Where are we now? Yes. Simple Rust. Okay, so this is a simple application. It doesn't have much to it. If we just compile it, oh well, if we look at the tasks, you don't even see any Rust task in here directly, unless I say all, because it just maps into the build cycle. So there are some tasks. You can see the plugin is still pretty young because it doesn't describe all the tasks correctly, but let's just run it, let's just build it. And hopefully this works. So a couple of things it does. It generates you a manifest, and one other thing it does, it actually allows you to process the Rust source before compiling it. So if you want to do pre-processing of the source code, it does, you can actually stick it into this phase, compiles it, and assembles it, and you can then run it. Now, it's a bit different to people that's used to Rust by the default. It always puts the artifact into the build Rust project directory. So you will actually, let's run tree on that, that's the easiest. Well, maybe I shouldn't have run tree on that, because that's all. Right. I effectively just, well, it created a TOML file. There's my source code. It actually processes source code, so it puts it in the build folder as well. And then actually builds it, because it didn't specify anything else. It builds a debug by default. And that's just all Rust temporaries. And eventually you end up with your executable. Okay. And if we look at that cargo file, it's a very basic one that is generated by default. Okay. It just puts the basic things in there. And it will figure out some reasonable defaults if you don't specify it. You can actually specify all those things in the Gradle file. Let's just pop out and go to another project before we run out of time. So I'm going to shoot through these ones. You can specify dependencies in Rust, or actually in Gradle for Rust. We just look at another file. Now we actually decided we want to depend on the MD5 crate, and this follows Gradle conventions. It actually sticks a special Rust handler into the dependencies block. If you do JVM development with Gradle, you're actually quite used to the dependencies block. And then that matches a common name that you find in configuration for Gradle as well. We just say for compilation, I need that crate, that version, and effectively, if you know Rust, anything that's Rust compiled maps to the dependencies block in the cargo TOML file. There are similar things for dev dependencies and build dependencies. And now I've decided to override the name of my project, so it's actually called Hello. And if I now build that, hopefully we'll retrieve this one again. That's the same kind of things. Takes a bit longer now because it has to install the crate. Okay, done. Let's scroll down. Now, did it build it? Oh, right. So there it is. It's creating me an executable. The other thing it does is similar to the native build. The outputs are hidden. So this is it. But if you want to see the outputs from your task, that's the error output from cargo and the standard output. So you can go and find it. If the build fails, it actually tells you where those files are. If it passes, it feels it doesn't have to tell you, because you don't probably care. Right, so we have one last example. That's all fine, but you might hate this, because you used the normal way of doing Rust. So you can actually build a Rust app. Just wrap around a normal Rust app, because that might be something you want to do. You might build a whole bunch of things. And people will all ask you, why do you want to build Rust with Gradle if you can build with Cargo? Well, that's the point. If you're just going to build a Rust application, you're probably just going to use Cargo. Same thing with most languages. But you're getting into multiple projects and polyglot environments. then you have to select your build tool very, very carefully. And this is actually one of the reasons why I think Gradle does a good job here. But anyway, let's go and look at our wrapped library. Now, we have a standard one here. Actually, I'm going to pop into that directory. That's probably easier to see. There we go. Let's treat that. Okay, that is a standard Rust project with an editable Gradle file. Okay, so you've defined your TOML file manually, and you've got your whole layout. So what you want to tell Gradle is, build this for me, and it can actually do more than just that, but let's fire off of that. So my last one here is wrapped grass. Look at this. So let's do my TOML file first. I just created one manually, and now what I do is still have my applied fee. Now, as I said, you can bootstrap Rust. So I'm just going to say my Rust executable has to be of version 124.1. It pulls it down the net. And it hides it somewhere in a folder, and it can actually keep multiple versions of Rust. So you can actually build, in the same two sub-projects, you can build the same application with two versions of Rust if you want. But this just goes to the point that you don't have to install things. I like that. Okay, now you have to tell it where the cargo TOML file is, and you have to tell it use cargo source layout. What I will actually do is I will read that file. You can still enhance it. If you want to put additional dependencies in, which isn't the TOML file, you can do it here, or you can override settings, but that's all you need to do, and you can actually bind an existing Rust project to Gradle. And I think we are on the dot 4 o'clock. Any last questions? Yes?
Plugins, how easy is it? You said that write the plugin interface was not the easiest. What would you actually write plugins in?
No, the plugins is actually relatively easy to write for Gradle. Typically, you would write them in Java, Groovy, or Kotlin. I write all of my plugins in Groovy, and I have them statically compiled as well. I think it's relatively easy, but as I said, I'm nearly done with the second book on writing plugins, so there's a lot of little tricks that you can learn. But generally, that's the phase you will go through. You'll do things in a file, and you'll find it grows too big, and you have this ways of farming it off, including Gradle files, which is not really that great. And then you have this special folder in Gradle called build source, which actually builds plugins specifically only for your project before it actually evaluates your project. So you can do fancy stuff in there. We've done it on one project, for instance, we build additional code narc rules and etc. And it then takes those code narc rules, apply them to the code narc plugin when it gets applied, and you have additional static code checking for your code, etc. So you can do lots of things. And then finally, if you decide, well, my plugin is useful for more than this project, you can actually convert it to a full plugin and publish it. It's a very easy process to do.
Can you decide where the dependencies go? You say they get hidden underneath, but can you put the dependencies outside of that project?
What do you mean?
So let's say here you say you're downloading Rust, for instance.
Yeah.
Or you can not go there and so that you can share it among projects.
Yeah, well, actually, what will happen is, I will show you for a moment. There we go. This is actually shared between all of my projects because it gets done properly. So you have a .gradle folder on your machine, every user. But we have this native binaries folder, and mine is probably going to be pretty big. Okay, so it caches the Rust binary in there, specific by version. See, I've got other things with caches, Node.js and Packer as well. But actually, let's list the Rust ones as well. So I think there's only one in there. Okay, currently I only have one in there. But it will create one for every version that you download, etc., and it will cache it in there. So all of your, actually, if two projects kick off the same time, the build, it will actually lock that folder. And then one of them will download it, and the other one can just reuse it.
What about support for kind of other C++ tools, let's say?
Well, this is same kind of thing that I showed you with Google test stuff. You have to pretty much pull it in. So you either have to do something that's going to pull it down as the binary, or you have to make it compile from source. That is where we really need cargo to solve a problem for us. Okay, good. Thank you.